welcome to this explainer. I'm absolutely thrilled to have you here today, because we're jumping straight into the heart of one of the most fascinating aspects of the physical universe, and that is electromagnetic induction. More specifically, we're going to explore why, when it comes to the invisible forces of electromagnetism, nature absolutely hates change. I mean, it actively and stubbornly fights back against it.
Okay, let's dive into this and ground ourselves in a really simple setup. Imagine a wire coil connected in a circuit with a meter, and there's a magnet right nearby. When that magnet just sits there doing nothing, no matter how insanely powerful it is, the meter is completely dead at zero. But the very moment you move that magnet toward the coil, boom, we get a reading. Just the act of moving the magnet forces the electrons inside the wire to move, which creates an electrical current. And that right there is electromagnetic induction.
But, this beautifully simple phenomenon brings up a really fantastic scientific mystery. And I want you to actually think about this for a second. When you move that magnet toward the coil and induce that current, the current itself creates its very own magnetic field. So here's the big twist. Will that newly induced current create a magnetic field that actually helps the magnet move along, or will it oppose the motion of the magnet?
Well, you might expect nature to take the easy road and kind of help the magnet along, right? But it actually fiercely opposes the motion. It's almost as if the universe is this incredibly stubborn character that just wants everything to stay exactly the way it is. If you try to alter the magnetic environment, the coil immediately fights back against whatever it is you're doing. It is a fundamental law of resistance.
Let's move to and see how this builds into a step-by-step physical reaction. Imagine you're actually doing this experiment yourself. Step 1. As you bring the north pole of a magnet toward the coil, the magnetic flux passing through that coil starts increasing. Step 2. This changing flux induces an electromotive force, creating a current. Now, Step 3 is where the magic really happens. According to Lenz's law, this newly induced current spins in a direction that creates its very own north pole right at the face of the coil. And because two north poles repel each other, the coil is actively pushing the approaching magnet away. You could literally feel the physical resistance in your hand. And then in Step 4, if you change your mind and try to pull the magnet away, decreasing the flux, the current instantly reverses direction. The coil's face becomes a south pole, trying to pull your north pole back. It pushes when you push, and it pulls when you pull.
All of this physical pushing and pulling is elegantly summarized mathematically in Faraday's law. It states that the induced EMF, that's the epsilon symbol, equals the change in magnetic flux over time. Now, what's really interesting about this slide is the right side of the equation. Specifically, look at that tiny little minus sign right at the front. In all of physics, that right there is the mathematical representation of nature's stubbornness.
That negative sign is the very essence of Lenz's law. It literally dictates that the induced EMF always, and I mean without exception, opposes the change in the magnetic flux that produces it. So it's not just some formatting choice for the mathematicians. It is the defining rule of how electromagnetism behaves. If the flux is increasing, the negative sign ensures the induced field subtracts from it. And if the flux is decreasing, well, it tries to add to it.
So the crucial point is that this tiny negative sign is not just some boring math you have to memorize. It is the absolute guardian of energy conservation in our universe. Just think about the alternative. If that sign were positive, moving a magnet toward a coil would induce a current that attracts the magnet, accelerating it further, which would induce even more current, which would accelerate the magnet even more. You'd basically have a perpetual motion machine creating infinite free energy out of nowhere. That single negative sign is the whole reason you actually have to do physical work, like burning coal, spinning wind turbines, or turning a hand crank to generate electricity. And this amazing phenomenon doesn't just happen in neat little wire coils in a laboratory either. It happens in solid conductors too. When a moving magnet induces currents in a solid piece of metal, like say a sheet of aluminum or a copper pipe, we call them eddy currents. Much like water swirling in a river, these electrical eddy currents swirl around inside the solid metal. And keeping perfectly in line with Lenz's law, they create their own magnetic fields that perfectly oppose the motion of the magnet that created them in the first place.
And this brilliantly illustrates one of the coolest real-world physics demonstrations you are ever going to see. If you take a really strong magnet and drop it down the center of a hollow copper pipe, it doesn't just fall at the normal speed of gravity. Instead, it falls much, much more slowly. Honestly, it looks like magic. As it drops, the moving magnet induces eddy currents in the copper wall below it, which create a repelling magnetic field pushing up against gravity. Simultaneously, the eddy currents above the falling magnet create an attracting field pulling it up. So the magnet eerily floats down the pipe as if it's moving through thick honey. It is just a stunning visual confirmation of electromagnetic induction happening right before your eyes.
It's an incredible visual for sure, but it really leaves us with a profound realization about the fabric of reality. I mean, what would happen to the delicate balance of the universe's energy if Lenz's law and that tiny mathematical negative sign just didn't exist? Our entire physical world, from how we generate power to light up our cities, down to the very laws of thermodynamics, is held together by nature's incredible built-in resistance to change. I'm going to leave you to ponder that strange and beautiful mathematical balance. Thanks so much for joining me on this explainer, and keep exploring the science around you.